Today, this is our podcast for consolidation. The announcements are that Homework 5 has been postponed to due on Monday, October 16th. Our basic skills test will be this next Wednesday on October 18th online. It'll be on 2D Flow and it'll be available all day. Homework 6 will be posted on Monday and it'll be due Friday, October 27th. And you can see the problems from the DOS book will be 10, 4, 7, 12, and 20. And today we're talking about compressibility and settlement. These are sections 11.1, 11.3 through 11.11 in our book with a course objectives 37 through 43. So this is where we are in the course. We're now talking about consolidation. And then the last topics will be shear strength and sampling methods and field methods. So the learning objectives for today will be to describe consolidation of fine-grained soils, identify factors affecting consolidation of soils, construct an analogy to illustrate load transfer in soils. We'll talk about primary consolidation and secondary compression, and then ultimately we'll develop a graphical representation of consolidation. So we talked about this last class on Monday, that if you have your initial conditions, and then you are going to, let's see here, add a footing. So you're going to increase the load at this location. And we talked about that also will cause something to happen to the soil. And we talked about how that increase in stress. So if this is located on a saturated soil, not only will there be an increase in stress at this location, but the particles themselves, the soil, will also have consolidation. A lot of consolidation concerns are when you're in urban areas, such as, for example, this is the I-15 reconstruction at Salt Lake City. It was one of the three major interstate exchanges that was constructed, and it was over 17 miles of roadway that was widened. And when you start to widen roadways, you have your original location of the roadway, and now you're going into places that haven't felt load before. So now you have to be concerned about differential settlement or differential consolidation. The Boston Central Artery Tunnel was another project in which we were digging in places that had a lot of soft clay, and they were building the tunnel through that area. So there's excavations where they are having unloading of soil, so that was changing how the stresses on the soil were behaving, and the soil was changing. And they also had additional, here's an example of unloading for the excavation. So when soils are either loaded or unloaded, you're concerned about consolidation and settlement. So when a soil deposit is loaded, for example, the structure or embankment deformations occur. And the total deformation at the ground surface is called settlement. If a load is removed, for example, excavation or melting of a glacier, then the soil can swell or decompress. So settlement is when the soil is loaded. There's three main factors. The first is what's the elastic deformation of the soil particles. Then we have the squeezing out of the air and the water from the void space and the reorientation of the soil particles. So as engineers, the main two things we're interested in is how much settlement, so the total settlement, and how fast, so the time rate of settlement. The components of the total settlement are the immediate elastic settlement, so that happens immediately when you add the load. Then the consolidation settlement, so that's time dependent, so that depends on how long it's going to take. And then as the water is removed from the saturation of the voids, and there's an effective stress change, and that's increasing in the pore water pressure. So PWP is pore water pressure. There's also another component called secondary settlement, and that's also time dependent, and this is due to the plastic adjustment of the soil fabric under a constant effective stress. So here's the equation for total settlement. It's the immediate elastic settlement plus consolidation settlement plus secondary settlement. The immediate settlement is caused by the elastic deformation of dry, moist, or saturated soils without any change in water content. In sand, it happens almost immediately. And in clay, it can occur, but it's small compared to the rest of the other two settlements. So in consolidation settlement, it's caused by the volume change, which is the saturated voids due to the expulsion of water. So in the past, we talked about compaction, and that was the removal of air. Now we're talking about consolidation. So this is a saturated soil, and the water is being pushed out. In clay, consolidation settlement is the most important. In sand, consolidation settlement occurs immediately because of the particles. There's not a lot of pore space. The pore spaces are fairly large, so water can move pretty quickly. Secondary consolidation occurs due to plastic rearranging of soil particles under the soil's fabric under a constant effective stress after the dissipation of pore water pressure. This occurs both in sand and clays and is dependent upon the mineral types present. So here's an example of a elastic settlement of a clay from a foundation. So you can see the contact pressure pushing down, and you can see the settlement profile for a flexible foundation. So the foundation is pretty flexible, so the profile is going to look like what is shown here. It's going to have this shape. But now if you have a rigid foundation that's not going to want to give a lot, here's the example of the contact pressure. But now the foundation, the settlement is going to have a shape that looks like this. In sands, you can see the different shapes. The flexible foundation has a shape that's shown in part A, and a rigid foundation is the same as it was before in B, but the contact pressure is different shaped. The modulus of elasticity is how the soil or material is going to respond to load. So you can see the different ES, the elasticity of the soil, modulus elasticity of the soil. You can see the different ranges. Soft clays have a very small modulus elasticity. Denser materials have very high ones. And the Poisson's ratio is how it compresses. So if typically the Poisson's ratio for an incompressible soil or incompressible material is 0.5, that means it doesn't change in volume when it's compressed. Typically you can see how the different ranges are for Poisson's ratios for soils, anywhere ranging from 0.2 up to 0.5. So consolidation, as we said, is when you load a saturated soil, so this is happening in saturated clays, the water is squeezed out over a long time. So here's how it looked like with time versus settlement. As you squeeze out the material, as you add the load, there's going to be this nonlinear portion of settlement, and then over time it's going to decrease in how fast it's changing. So this can take very many years. In granular soils, or that'd be gravel and sand, when you first put the load on, it occurs very quickly. So this is where the load is going to occur, and you add the load and you're going to have immediate settlement. This is the immediate settlement, and then it doesn't really change with time. And that's due to the high permeability of the material because it has large void spaces. So once again, we said that we need to ask questions such as how much settlement, how much the magnitude of ground deformation, how quickly will the settlement occur, that's the rate, and what is the spatial distribution of the settlements, differential settlement. We're mostly focusing on clay soils because they're common in a lot of major urban areas, Chicago, San Francisco, Boston, Mexico City, Singapore, Hong Kong, and they can slow settlement rates can damage constructed facilities. So as the load increases, you're increasing the grain contacts. Remember the increased grain contacts, that is our effective stress. Then we're expelling water, so that is changing the void ratio. So now the voids are getting smaller. That leads to a volume change, which ultimately leads to deformations. So here's what this would look like graphically. So we know that it's time dependent. Water is flowing out of the matrix. There's a change in effective stress. That's how the particles are interacting with each other. And there's a change in the volume. So if you look at all of these different parameters with time, let's look what happens. First we load. When we load the soil, that's the total stress. When we're increasing the stress, we're going to immediately have a lot of pore water pressure. The pore pressure is going to carry a lot of the load. And then, so that's the change in stress we just added to our soil. And then with time, we're not changing the stress, the total stress. This is the same load that's been applied to the soil, but now the pore water is starting to dissipate or leave the soil. It's able to find its way out through the pores, and over time is going down to zero. The effective stress, so the contacts between the pores, is now going to increase, and that's going to cause a volume change. So if you imagine what this looks like, we have our pores touching, pushing against each other, and when we first load it, the water that would be in between here is carrying most of the stress. As that water finds its way out, so it's going to find its way to a drainage path and leave, it's going to decrease the pore pressure. So the pore pressure, U, is decreasing. That's what this is, U here. And now the contacts, the effective stress, sigma prime, is going to increase with time. And also these voids are getting smaller. So the water's leaving, and now we're going to have smaller voids. The spaces between are getting smaller, so that means the volume is changing. It's decreasing. So you can see here the volume change. This is showing that this is, if this would be positive for increasing, this is showing that it's getting smaller. So if we think about this as an idealized spring model, imagine that you have a container full of water. So here's our container, and it's full of water, and it has a spring. In this case, the spring is going to represent our soil skeleton, what's carrying the load. The water is going to represent the water that's inside the pores. So when you first have a stress added to this, and our valve here is like the porosity. It's what controls how fast the water can leave. So at equilibrium, this will be our initial static pore pressure. And this is what the soil would be like. All of it's being carried by the spring. Now, if we add some load, so we're adding load here, what's happening is that when we immediately add it, the water cannot escape that fast. This is a very small opening, so water can't escape very quickly. So you have this excess of pore pressure, and all of the load is being carried by the water. So all of the load is being carried by the pore pressure, and very little of it is going by the soil structure. But over time, the water is able to escape through this valve or through the pores, and now the water pressure is decreasing, the load is being transferred to the spring, and the piston goes down, creating settlement. So you'll notice that initially there was very little settlement because the water is carrying pretty much all of the load, and very little water could escape. But as we give it time for the water to come out the valve, it starts to decrease in its volume. So it has a change in volume, and instead of the water carrying the load, the spring is, which was basically the soil structure. So what's happening is, as I said before, you have your particles touching each other, and as the water dissipates the pressure, as that water is able to leave through the pores, these contacts are going to increase and carry more of the load over time. And this takes a long time because there's very little tiny voids, and for them to find their way out takes a long path. So here again is the plots. It's important to know how to plot these and explain what they are. This is the graphical representation of consolidation, and you can see what they look like and how to label them. So lastly, we're going to talk about how do you test this, how do you get this information. So if you're in the field, you would take a specimen. So here's our undisturbed specimen, and we take it to the lab to run what's called a consolidation test or odometer test. And basically what we do is in the lab, we're going to trim the specimen, put it inside this metal ring, and we're going to put it inside of a testing odometer. So here's what they look like. This is where your specimen or your soil is in the center. You're going to trim it to fit inside this ring. You'll have porous stones on the top and bottom so that you can load your specimen, and water is going to be able to go up and down through the porous stones. And we're going to measure, we'll have a dial gauge here. When we're loading it, we'll measure with a dial gauge how much it's changing in height. So there's two different types. There's the floating ring and the fixed ring. The main difference is the floating ring is not attached at the bottom. The ring is not attached to the bottom of the base, whereas this one you can see that the fixed ring is at the bottom of the base. So the reason this is important to test is that most materials act linearly, whereas clays are nonlinear. So as we load it, so this bottom axis is our stress. Notice it's a log scale. And this is our void ratio. Remember, that's related to the volume of the voids and the volume of the material. So as we load, we're going to increase our stress and we're going to decrease our void ratio, which means we're going to make the void smaller and smaller. But notice this is not linear. has a curve in it. As we unload, which we can also do, which we remove the stress, that's going to decrease. But now it can swell. The material will want to rebound and the water will want to come back in between the voids and push the material back out. So that is what a consolidation test will look like and the type of data that you will ultimately get. Here's another example of an odometer test. Notice that we're in log scale, but this is what it would look like if you're in an aromatic scale. So if it would be have not as much of this curve that you see in this log scale. There's two types of parameters that you'll calculate that are important to understand that you get from the data. The first is called C sub C. That's the virgin or primary compression. And then there's also C sub R, which is the recompression index or unloading index. And both of those are calculated as slopes. So the first one, C sub C, is the slope of the main line, the loading line, and the C sub R is the slope of the unloading or the reloading line. And we'll work some examples of how to calculate this in class and on the videos. So how do we get this information and why is it important? Well, why it's important is that over time, the soil's been loaded or unloaded and it responds based on its past history. So imagine here's our soil and we're interested in this spot. So as we load, say that a deposition occurred, that a lot of sediment was added. So this is in the ocean, this is all saturated. Say this is back in when everything was covered in water, and you have your soil, and now you've added some soil. What's happening is as we move down, this is the stress axis, and we're changing void ratio. We're adding load, and it's getting more, the void ratio is getting decreased. And if we add a lot more, it keeps going down. And then if we unload, say that this is erosion. So say that we had deposition, a big amount of deposition, and then some of the material was lost due to erosion here. This is what's happening here. Then we're decreasing that stress and we're unloading the material, so we're rebounding. If we keep doing that, we'll keep moving up the rebound curve. And if we go back to the compression and have the same material as we had before, the soil remembers where it was in its past. So that's why it's back to the same level as it was in the past. And if you keep going, it'd stay on the same line. So that's the interesting thing about soil is it actually knows what it's had in its past and can remember where it's been and how it responded in the past. Another type of thing you need to be aware of is what's called sensitivity. It's when very soft soils or soils can basically be poured like a liquid once they've been disturbed. So for example, in Norway and some places that have quick clays, it's when the soil is stable until it's basically been remolded. And then the term thixotropy is when the material gains strength after it's been remolded. So here you can see in the picture, this is an undisturbed clay, and you can look at how much stress or load it can carry. But then when someone stirred it, it can basically carries no load and it's basically liquid. So that's what sensitivity is. And here's an example of a consolidation test for sensitivity. You can see that it'll carry stress up to a certain point and then it has a very sharp turn where it no longer can carry any load. Here's an example of some different curves, and typically a lot of marine soils are sensitive. Here's collapsible soil, so less in Iowa is very sensitive to consolidation, and you can see that it's sensitive to when it's wetted because of its bonds. And so when you start to load it, if you add water to it, once you start loading it, it can collapse. Here is just some examples of different types of correlations, just so that if you ever wanted to look at different data, compare data from what you have from your reports and verify it seems accurate, you can look at different data. Here's the ranges that is typically within. Here's examples of sand. So consolidation does happen in sand, but it happens very rapidly. And it's a function of the shape of the particles, their gradation, so well or poorly graded, if it has any fine materials like silt or clays on there, and it can also, if you load it enough, the materials can actually crush and the particles can become smaller because of the crushing. Here's examples of compressibility of sand. Since there's so many factors, there's not really good correlations. So finally, this is a combination of all the plots we talked about combined into one. So if you add the load, you're going to have this decrease in pore pressure with an increase in effective stress. That's what that looks like. And we just talked about consolidation, so we'll continue with 1D consolidation in class.